With Nagaro's diverse range of resilience engineering services, you can build robust and reliable systems and ensure business continuity. Our tailored solutions ensure that your brand has the unbeatable advantage of staying at the top, even during unforeseen events.
Right. So, hi everyone once again. I'm Sarthak Jain, a senior software developer at Harness and maintainer at Itmus Chaos project. I know it's a bit late for some of you out there, but if you are with us, that means you're surely enjoying the Chaos Carnival. So, we have yet another interesting session, and for this, we have with us Jay Desai, Tanveer Gill, and Karanveer Sohi from FluxNinja, who will be talking about graceful degradation, keeping the lights on when everything goes wrong. So, yeah, this is going to be a recorded session. But yeah, we have these folks with us just to answer if you have any questions and have a chat with them at the end.
Good day, everyone. Are you ready to learn how to keep your systems up and running even when everything seems to be falling apart? Hi, I'm Tanveer Gill, CTO of FluxNinja, and I'm thrilled to be here today to share my insights on graceful degradation. As operators and practitioners, we all know how challenging it can be to maintain the stability and performance of complex microservices. Even with the best design practices in place, failures are inevitable, and when they happen, they can cause chaos and disruption. That's why today I want to talk about a practical approach to managing failures called prioritized load shedding. By prioritizing which workloads or users receive resources during a degraded state, we can ensure that critical user experiences are preserved and our services remain healthy and responsive. Not only does this approach help prevent cascading failures, but it also allows you to maintain critical services even when resources are scarce. Throughout this presentation, I'll help you build an intuition about load management by starting from basic principles of queuing theory and Little's law. These concepts are universally applicable to any system that serves requests, making them valuable tools in your arsenal. So let's dive in and learn how to keep the lights on even when everything else is failing. And if you have any questions, feel free to reach out to me on LinkedIn or Twitter. I've shared my handles on this slide. Let's take a look at what we'll cover in this presentation. We'll start off by exploring the dynamics of overload from the perspective of a single service. We'll discuss the factors that contribute to overload and how it can impact your systems. Next, we'll delve into the benefits and challenges of implementing concurrency limits in a microservices environment. We'll examine real-world case studies to see where concurrency limits help prevent outages and where a lack of limits caused prolonged downtime. In the third part, we'll introduce you to Aperture, an intelligent load management platform. We'll demonstrate how Aperture's dynamic concurrency limits can improve service performance under heavy load. In the final part of our presentation, we will discuss what a complete load management strategy looks like and show how Aperture's declarative policies can help you express these strategies in a centralized manner. By the end of this presentation, you'll have a deeper understanding of how to implement graceful degradation in your microservices architecture and the tools you need to keep your systems running smoothly. So what happens when a service becomes overwhelmed? The top of the diagram depicts a healthy service under normal load with a steady response time. However, when the service becomes overloaded, requests start to back up and response times skyrocket, eventually leading to timeouts. This is depicted in the lower part of the diagram. Through load testing, we can determine the concurrency limit of a service, which is the maximum number of requests a service can process in parallel before response time starts to deteriorate. The reason for this limit is the finite nature of underlying resources and can manifest as bottlenecks due to thread contention, context switching, garbage collection, IO contention, and so on. But no matter how complex the inner workings of a service might be, it can still be modeled through Little's law, which states that L, the number of requests in flight, is equal to lambda, the average throughput, multiplied by W, the average response time. By applying Little's law to a microservice, we can determine the maximum average throughput, lambda, that a service can handle before it becomes overwhelmed. Once the number of requests in flight exceeds the concurrency limit of a service, there is an inflection point where excess requests begin to queue up, leading to an increase in response time latency. The following chart illustrates the impact of a service becoming overwhelmed. The x-axis plots the throughput of incoming requests, while the left y-axis shows median latency and the right y-axis shows availability, represented as the proportion of requests served within timeout. As shown in the left portion of the graph, as long as the number of requests in flight stays within the concurrency limit, the latency also remains normal. Once the concurrency limit is reached, any increase in throughput contributes to an increase in latency as a queue begins to build up. The availability line measures the number of requests served within the timeout limit. Once the median latency becomes equal to timeout, the availability drops to 50% as half of the requests are now timing out. As throughput continues to increase, the availability rapidly drops down to zero. This chart demonstrates the critical importance of managing load in a service to avoid latency spikes and ensure that requests are being served within the desired time frame. In highly interdependent microservices architectures, localized failures can quickly cascade to other parts of the system, and lack of an effective load management strategy at a service can quickly lead to cascading failures and complete system outage. By taking a proactive approach to load management, you can help prevent these type of catastrophic failures. Now we do understand what happens to response times when a service gets overloaded, but what causes a service to get overloaded in the first place? In a modern app composed of a large number of services, each service is provisioned to support a certain level of demand. If demand always matched perfectly with provision capacity, load management wouldn't even be required. However, the real world is dynamic, and demand can quickly outstrip available capacity, leading to service overload. Some common causes of service overload in production include unexpected traffic spikes during new product launches or sales promotions. These spikes in traffic can quickly overwhelm a service that is not prepared to handle the increased load. Another reason could be service upgrades that introduce new bugs or performance regression that lead to slower response times. The regular incoming load might exceed the provision capacity when this happens and cause overloads. Another reason could be upstream services or third-party dependencies slowing down. So this can cause requests to back up and lead to an increase in response time latency at the dependent service. Retries can actually lead to an interesting failure scenario known as metastable failure. This happens when an initial spike in load puts the system under a permanent state of overload. The service stays overloaded even long after the initial spike has passed. The initial trigger can also be an intermittent service failure, but the end result is always a retry storm that amplifies the load on the service, which leads to a state of permanent overload. The last two are examples of localized failure leading to load amplification. When a localized failure occurs in a service, it can cause an increase in load on other parts of the system. For example, a cache failure can lead to a higher load on the database, or a subset of servers going offline can cause excess load on the remaining servers, say when the load balancer actually rebalances the traffic to other healthy instances of the service. Understanding the causes of service overload is useful to appreciate the need for an effective load management strategy. In the next part of our presentation, we'll explore how concurrency limits can help protect services from overload and examine real-world case studies. In this section, we'll explore how to optimize the availability and performance of a service using concurrency limits. The idea is to set a maximum limit on the number of in-flight requests a service can handle at any given time. Any requests beyond that limit would be rejected or load shed. By setting a concurrency limit, we can ensure that the service remains performant even under high rates of incoming traffic. This approach is based on the assumption that we have a clear understanding of the maximum concurrency limit that the service can support. Let's take a look at how concurrency limits can help preserve service performance. The following chart provides a visual representation of this concept. On the x-axis, we have the incoming throughput of requests. The left y-axis shows the median latency, while the right y-axis shows availability, which is represented as the proportion of requests served before the timeout. As shown on the chart, the availability remains at 100%, even when incoming throughput becomes much higher than what the service can process. This is due to the fact that any access load is shed because of the maximum concurrency limit set on the service. This means that the service can continue to perform optimally even during high load. The chart demonstrates how concurrency limits can help us preserve performance and availability for our users, even in the face of high traffic. In the next part of our presentation, we'll examine the challenges of implementing concurrency limits in a constantly changing microservices environment. And we will also review real-world case studies to see where concurrency limits helped prevent outages, and where a lack of them caused prolonged outages despite techniques such as autoscaling. Google once ran a service with many millions of mobile clients that cached users' state on their mobile devices about images that were incrementally uploaded to a backend storage service. This backend storage service was configured to automatically shed requests once it reached its predetermined maximum capacity, starting with the lowest priority requests and then working its way up. However, a new app release was pushed to the clients that had the unfortunate side effect of resetting the record of which data had already been uploaded. This bug made all the clients try to connect to the service at once to re-upload all their data. Despite this orders of magnitude increase in incoming traffic, load shedding helped keep the service available. By shedding the lowest priority requests, the service was able to stay within its concurrency limit and remain responsive to higher priority requests. This case study demonstrates how concurrency limits can help prevent service overload and preserve availability and performance even in the face of unexpected traffic loads. The second case study is from Niantic at the launch of Pokemon Go, a mobile game whose success greatly exceeded all expectations. Their load balancing layer became a bottleneck, so they had to migrate to Google Cloud Load Balancer. However, the migration simply resulted in overwhelming their backend stack, making it extremely slow. As backends failed, the Pokemon Go app attempted to retry failed requests on behalf of the users. At the time, the app's retry strategy was a single immediate retry followed by constant backoff. As the outage continued, the service sometimes returned a large number of quick errors, for example, when a shared backend restarted. These error responses served to effectively synchronize client retries, producing a thundering herd problem in which many client requests were issued at essentially the same time. This was a classic load amplification situation. This case study illustrates that reactive and isolated scaling cannot offer protection in case of overload. Protective techniques such as concurrency limits and prioritized load shedding could have helped maintain availability and ensure that services continue to serve at their provisioned capacity while scaling gets performed in the background. While concurrency limits are a powerful technique for managing load and ensuring service availability, implementing them in a dynamic microservices environment presents several challenges. Some of these challenges include determining the optimal capacity limit for each service, which can vary depending on the nature of the workload and available resources. Setting the limit too low can result in requests being rejected even when the service has plenty of capacity, while setting the limit too high can lead to slow and unresponsive servers. Another challenge is monitoring and adjusting concurrency limits as traffic patterns change. For instance, imagine a database API which is write heavy. The concurrency of a service hosting such an API is going to be sensitive to the relative mix of reads versus writes, and there could be constant need to adjust the concurrency limits as the traffic patterns change. Next is ensuring that concurrency limits do not interfere with other operational concerns such as autoscaling. Another concern is coordinating concurrency limits across multiple services and shared resources. And last but not the least is observability. How do you provide real-time visibility into the state of the system and the effectiveness of concurrency limits? To overcome these challenges, it's important to have a comprehensive and scalable load management solution that can automate the process of setting, monitoring, and adjusting concurrency limits in real time. Not all requests are created equal. Some are more important than others. For example, requests from paying customers should be prioritized over those from free users, and user-facing requests should be served with better SLAs compared to background requests. Additionally, business-critical APIs should take priority over non-critical ones. But before we can prioritize requests, we need to rank them based on their relative importance. And in order to do this, we need to know the cost of admitting each request, that is, how many server resources it will consume. To achieve all this at scale, we need a way to classify and prioritize requests in a service-independent and generalized way. And also, we need to automatically estimate the cost of admitting various types of requests. Solving these challenges will help us optimize the performance of our services and provide better services to our users. In the next section of our presentation, we'll explore how Aperture, an intelligent load management platform, can help overcome these challenges and implement concurrency limits at scale. Aperture is an open source platform for intelligent load management that helps manage the performance and availability of microservices in a dynamic environment. Here is a high-level overview of its features. Aperture provides a declarative policy language visualized as a circuit graph, enabling easy configuration of policies. Aperture allows you to perform workload prioritization, concurrency limiting, distributed rate limiting based on arbitrary keys, and service autoscaling. All of these techniques enable effective load management of services to make sure they remain performant despite failures. Aperture integrates with popular language frameworks, making it easy to adopt Aperture for existing applications. Aperture also provides seamless insertion via service mesh such as Envoy, making it easy to insert Aperture without modifying service code. Aperture offers a suite of powerful features to help manage microservices in a dynamic environment. It provides intelligent workload classification. Aperture can automatically classify requests based on their priority and cost, allowing for dynamic prioritization and load shedding. Aperture offers dynamic concurrency limits. Aperture can automatically adjust concurrency limits based on real-time traffic patterns and service level objectives, ensuring that services stay performant even during high loads. Aperture has circuit-based policies. Aperture uses circuit-based policies to describe load management strategies as control systems. Aperture offers distributed rate limiting, which allows for more accurate and efficient rate limiting across microservices. Aperture has auto-scaling capability. Aperture can automatically adjust the number of instances of a service to match traffic patterns and even performance goals. And lastly, Aperture offers real-time insights and analytics. Aperture provides real-time visibility into the state of the system and the effectiveness of load management policies for explainability and debuggability. Each signal in the policy circuit is available to be plotted as a Prometheus metric. Aperture also provides live preview APIs to view attributes from live requests. It can also export summarized logs with request attributes as OLAP data into a database like Druid. Aperture is built on a distributed architecture that provides a unified observability and controllability platform for cloud-native applications. The architecture is designed to ensure high availability, scalability, and reliability. The Aperture controller is the central component of the platform. The controller monitors the system using an inbuilt telemetry system and collects metrics on service performance and workloads, including information on customer tiers, request types, and other relevant attributes. The controller uses declarative policies expressed as control circuit to analyze the collected metrics and make decisions on load shedding, flow control, auto-scaling to ensure that the application operates within the specified SLOs. The policies are based on the principles of observability-driven closed-loop automation, which continuously tracks deviations from service-level objectives and calculate recovery or escalation actions. The controller's policies are stored in a policy database and can be managed using the Kubernetes custom resource definitions, allowing users to easily configure and modify policies as needed. Next up, Aperture agents are the workhorses of the platform, residing alongside service instances as sidecars or daemon sets or virtual machine agents. They provide powerful flow control components such as a weighted fair queuing scheduler for prioritized load shedding and a distributed rate limiter for abuse prevention. The agents monitor golden signals such as request latency, error rates, saturation, using a built-in telemetry system and a programmable high-fidelity flow classifier used to label requests based on attributes such as customer tier or request type. Aperture agents schedule workloads based on their priorities, helping maximize user experience or revenue even during overload scenarios. Agents integrate with service meshes or can be used with SDKs to provide flow control capabilities. Additionally, agents work with auto-scaling APIs for platforms such as Kubernetes to help scale infrastructure whenever needed. Aperture uses two databases to store telemetry and configuration, Prometheus and etcd respectively. Prometheus is a time series database used to store and query telemetry data collected from Aperture agents. It enables Aperture to monitor the system and detect deviations from the service level objectives defined in the declarative policies. etcd is a distributed key value store used to store configuration and flow control information. Aperture controller uses etcd to store the declarative policies that define the control circuits and their components, as well as the current system state. By utilizing this architecture, Aperture provides a scalable, flexible, and intelligent platform to manage workloads at scale, including dynamic concurrency limits and workload prioritization. The diagram on this slide shows how Aperture Agent interfaces with your service to implement dynamic concurrency limits. Aperture agents run alongside your services, and on each request, the service checks with the Aperture agent whether to admit the request or drop it. The Aperture agent then returns a yes or no answer based on the overall health of the service and the rate of incoming requests. Aperture uses a token bucket algorithm to limit the concurrency admitted into a service, ensuring optimal performance and availability. To prioritize workloads, requests are classified based on attributes and assigned arbitrary labels. Aperture then automatically calculates the cost of admitting each request by isolating the latency profile for each workload. Aperture's weighted fair queuing scheduler prioritizes requests in a fair manner without causing any starvation. For example, you can specify that requests to URI/checkout have a higher priority than requests to URI/recommendation, or that subscribed users should be allocated a greater share of resources compared to guest users. Aperture Scheduler will then automatically allocate resources accordingly, optimizing both user experience and resource utilization. This approach helps ensure that services remain performant even during high traffic and can adapt to changing workloads and dependencies. With Aperture, implementing dynamic concurrency limits becomes easy and effective. Let's simulate a test traffic scenario to demonstrate the effectiveness of Aperture's concurrency control policy. Our service is designed to serve up to 10 users concurrently. Using K6 load generator, we'll alternate the number of users below and above 10 to simulate periodic overloads. This will show how Aperture dynamically adjusts the concurrency limit based on service health. The app receives traffic from two types of users, subscribed and guest, which can be inferred from the request headers. We'll simulate an equal number of guest and subscribed users in the traffic. We'll configure an Aperture policy to assign 4 times the priority to subscribed users compared to guest users. This will show how Aperture's workload prioritization feature works to allocate resources and provide fair service to both types of users. Let's take a closer look at how Aperture's concurrency control policy can improve service performance and workload prioritization. This is particularly important in dynamic environments where sudden loads can cause service degradation and outages. The first panel shows the response time of the service, while the second panel displays the count of different decisions made by Aperture agents on incoming requests. The left part of the chart highlights the issue of high latency without Aperture in place. However, once Aperture's policy is in place, it dynamically limits the concurrency as soon as response times start to deteriorate. As a result, the latency remains within a reasonable bound. So this is with Aperture providing active protection. The second panel shows the breakup of requests that were accepted or dropped by Aperture when the policy is applied. The blue and red line indicate the number of requests that were dropped for guest and subscribed users respectively. The yellow line in the second panel represents acceptance rate for subscribed users, whereas the green line represents acceptance rates for guest users. As can be seen, during the overload condition, subscribed users are getting roughly 4 times the acceptance of guest users. And this is despite that we have equal number of incoming requests for both subscribed and guest users. So this demonstrates the effectiveness of Aperture's workload prioritization mechanism. In summary, this policy improves service performance and protects against outages and degradation by dynamically adjusting concurrency limits and prioritizing workloads. Now let's explore what policies in Aperture look like. Aperture policies are built using a circuit graph, a declarative policy language that makes it easy to configure control loop logic. These policies can also be used as ready-to-use blueprints that can work with any service. The policy being shown adjusts the concurrency limit of a service based on response times, which is an indicator of service health. Let's take a closer look at how the circuit works. On the top left, you can see a PromQL component that queries the response time of a service. Then this response time signal is trended over time using an exponential moving average. The current value of the response time is compared with the long-term trend computed by the exponential moving average to determine whether the service is overloaded or not. These signals are then finally input into an AIMD concurrency control component, which controls the concurrency. This control component is inspired by TCP congestion control algorithms. It gradually increases the concurrency limit by ramping up the throughput. If the response times deteriorate, there is a multiplicative backoff in place to prevent further degradation. The flexibility of these circuits allow you to configure load shedding to be based on another metric, such as queue size and RabbitMQ, for instance. You can also detect overload at an upstream service and load shed at a downstream service in order to reduce the wasted in-flight work. Using Aperture's policies, you can easily manage and optimize the performance of your microservices, ensuring that they remain performant and available even under high traffic conditions. Aperture circuit policies enable a unified control system for load management and autoscaling. Load shedding is a crucial technique for ensuring the performance and availability of services under high load. When a service becomes overwhelmed, load shedding can be used to prioritize critical workloads and drop non-essential ones. However, if load shedding is used in isolation, it can cause problems for autoscaling. For example, if a service is shedding requests due to high traffic, but the resource utilization remains stable, an autoscaling policy based solely on resource utilization may not trigger additional instances to handle the load. By incorporating load shedding as a signal for autoscaling, we can create a more effective automated response to changing traffic patterns. Building on the previous circuit, we can use load shedding as a signal for autoscaling. When this circuit detects that the service is shedding requests due to high traffic, it can trigger autoscaling to spin up additional instances to handle the load. This unified control systems approach allows for a more effective and responsive approach to load management and autoscaling, improving the overall performance and availability of cloud-native applications. Load management techniques fall along a spectrum of proactive to reactive approaches. At the proactive end of the spectrum, we have preventive techniques such as rate limiting, which aim to prevent issues from arising in the first place by limiting the impact of heavy users abusing the APIs. Moving along the spectrum, we have protective techniques such as adaptive concurrency limits and prioritized load shedding, which are designed to minimize the impact of service outages or degradation events. These techniques help ensure that services remain available and customer experience is maintained during and after an outage or degradation event. Finally, at the reactive end of the spectrum, we have escalation and recovery techniques such as autoscaling and rebalancing traffic across regions, which help to quickly resolve issues, minimize downtime, and maintain service availability. By implementing a combination of these techniques, we can create a complete load management strategy that can adapt to changing workloads and dependencies, while ensuring high availability, scalability, and reliability of cloud-native applications. To be effective, these strategies require centralized awareness and coordination, which is a control systems problem. Aperture's control systems approach provides a unified platform for implementing these load management strategies. Thank you for joining us for this talk on graceful degradation and the importance of load management and microservices. We hope you have gained valuable insights on how to improve the reliability of your microservices through techniques like concurrency limits and load shedding. As we have seen, these load management strategies are crucial for preventing outages and maintaining optimal performance in dynamic environments. And with Aperture, we have a powerful tool for implementing these strategies and automating load management at scale. We encourage you to check out the Aperture project on GitHub and start exploring its capabilities for yourself. Your feedback and contributions are vital to the success of this platform and the wider microservices community. Together, we can build more resilient and reliable systems that keep the lights on when everything goes wrong. Thank you.
Right, yeah, that was a great session, Tanveer. So looks like people have enjoyed it a lot. And we had one question as well in the chat. So, I see you have already answered that. Do you want to take it here on the stage?
Yeah, sure. Glad to do that. So the question for the audience was like, how does like the concurrency limit approach compare to circuit breakers? That's a great point. Like circuit breaker is another protective technique, which it's like a client-side technique which looks at errors, latency, essentially degradation in service response times and response codes to trigger a circuit breaker. Essentially, like you see circuit breakers in electrical circuits all the time, where let's say the amperage, the current goes beyond a certain point. It basically opens the circuit. No current flows after that. It's the same technique. So no requests flow once that threshold is hit. So it's more of a heavyweight approach. It's not a very fine-grained approach compared to what I just showed you. So it completely stops all requests at that point. Whereas the adaptive concurrency limits does it more intelligently, so it maximizes throughput, good throughput. So while you're under load, it's maximizing the amount of so whatever you're provisioned, so it's making sure it's getting the maximal throughput possible. And on top of that, you can prioritize requests. For example, you can prioritize paid users or subscribed users, or certain critical APIs. Let's say you have a checkout API. Let's say you're an e-commerce site. You don't want your checkout APIs to ever fail. Whereas something non-critical like a recommendation API can actually get load shed. So you can program all that using this technique. That's how it's different. Yeah.
Right. Thanks for answering this, Samir. I hope you have got your answers, Saranya. So that was the only one question that we had, and all right, yeah. So it's like she has got the answer. All right. Also, we are good with the time. So yeah, this was the last session for us today. We have an ending note lined up next. Yeah. Once again, thank you so much, Tanveer, Karanbir, and Jay for this session
Yeah, player. Yeah. Thank you.
and this.